Um, Let me begin by just putting on the table a hypothesis that it'll be useful to refer to later on in the talk. Hypothesis that should have had a name a long time ago. Why don't we call it the fundamental hypothesis of statistical mechanics? Here it is. Consider a true thermodynamical law, any true thermodynamical law, to the effect that macro condition A evolves under such and such external circumstances and over such and such a temporal interval into macro condition B. Whenever such a law holds, the overwhelming majority of the volume of the region of phase space associated with macro condition A, according to the standard Lebesgue measure, or what people are now sometimes calling the Louisville measure, on the phase space of the system in question. So let me read that again. Whenever such a law holds, the overwhelming majority of the volume of the region of phase space associated with macro condition A on these standard measures is taken up by micro conditions which are sitting on an interval through the region of phase space associated with macro condition B. Good. It seems like not much of an exaggeration to say that the whole science of statistical mechanics, going back to the pioneering work of Boltzmann and people like Gibbs as well in their own way and so on, is aimed at making it plausible that precisely this hypothesis is true. Proofs, of course, are out of the question, or Gentile proofs are out of the question for people who've been in classes of mine. Proofs are out of the question, except in the simplest and most restricted sorts of situations, but let's put that aside for the purposes of this particular conversation and simply assume from here on that the hypothesis is indeed a theorem of Newtonian mechanics. Good. Now consider a postulate, the one that Value was talking about, call it the statistical postulate, that runs like this. Take an arbitrary thermodynamic system called S and some arbitrary possible macro condition of S called A, and let capital R sub A be the region of the phase space of S that's associated with the macro state A, and let little r sub A be any subregion of big R sub A. Then the probability that the micro condition of S lies in little r sub A, given that S is in the macro condition A, is equal to the standard Lebesgue volume of capital R sub A divided by the standard Lebesgue volume of little r sub A. Excuse me, it's the other way around. Of little r sub A divided by capital R sub A. If the statistical postulate, the one I just stated, is true, and if the fundamental hypothesis of statistical mechanics is true, then the two of them together will straightforwardly, logically entail, the two of them together will straightforwardly explain the truth of the modern probabilistic versions of the laws of thermodynamics. And note here, and this is going to be important throughout the talk, the explanandum that I want you to have before your imagination is not this or that particular event, but the sort of probabilistic version of the second law of thermodynamics. Good. Good. Now, everybody knows that there's a famous trouble with this explanation, the one that Value mentioned again, which is that it works just as well going backwards. The trouble that is that the fundamental hypothesis and the statistical postulate taken together are going to entail not only that the half-melted piece of ice in the glass in front of me will very likely be more melted in 10 minutes than it is now, which is correct, but also that it was very likely more melted 10 minutes ago than it is now, which is preposterous. But put that aside for the moment, just as Value did, so our talks have a lot of structure in common. Indeed, I saw hers and was imitating it. Put that aside for the moment. It has nothing directly to do with the main business of this particular discussion, and it'll be easy and very straightforward to come back and fix it up once our main present business has been attended to. What I mainly want to talk about, what both Value and I guess, came here to talk about, is the nature of the statistical postulate. And this is a matter about which There have been lots of disagreements in the scientific and philosophical literature. And those disagreements continue to bedevil us even now. Good. Let me start, if for no other reason than to have something simple and explicit on the table, with what I understand to be the right story. And this is, once again, this is not original, this is trivial. Just in Valia's talk, we had a brief allusion to what Jean Bricemont's attitude seems to be. The arguments aren't the same, but the end attitude seems to be very similar to the one I'm about to describe, which is this. The statistical postulate is an empirical law of nature, and we come to believe in the statistical postulate in much the same way and for much the same sorts of reasons as we come to believe, say, in this or that particular set of microscopic laws of motion. Reasons like empirical adequacy and explanatory power and elegance and simplicity and so on. And it follows that the statistical mechanical explanation of the modern probabilistic form of the laws of thermodynamics, if this is right, rests, as Valia was saying in the setup, which she was then going to take down, rests on two completely separate and logically unrelated empirical premises: the microscopic laws of motion and the statistical postulate. Neither of those on its own is going to suffice, but the two of them taken together, if we're to believe the encouragements of Boltzmann and Gibbs, can do the job. And the disputes that Valia and I both came here to talk about have to do with a long tradition that she was talking about too, of suggestions to the effect that the laws of thermodynamics in their modern probabilistic form can somehow be obtained from or described in or dug out of the underlying microscopic laws of motion alone. They have to do, that is, with one way or another of imagining that the other premise of the argument, the statistical postulate, if one can only see it aright or say it aright, amounts to almost nothing. That it amounts, for example, to an a priori principle about how to reason, or an a priori principle about where the business of explaining properly comes to an end, but not on any substantive claim over and above the dynamical laws themselves about the actual empirical nature of the world. Here's a famous, old, and paradigmatic example, a principle of indifference. There's a thought that goes back, I guess, at least as far as Laplace. Probably a lot of people here know the history better than I do, that runs like this. Suppose that you know that a certain physical system is in one or another of a certain collection of n different possible physical states, and suppose that you know absolutely nothing more about the state of the system than that. Then there's an a priori principle of reason, a so-called principle of indifference, to the effect that you ought to proceed as if the probability that the system is in any particular one of those states is 1 over n. And the application of a thought like this to statistical mechanics is presumably going to run as follows. If all I know about a certain system is that it's in a certain particular macro condition, then I know that it's in one or the other of the micro conditions with which that macro condition is compatible. And I know absolutely nothing more about the macro condition of the system, of the micro condition of the system than that. And if we pretend for a moment that all we ever do know about the conditions of thermodynamic systems are their macro conditions, this is false, but make believe it's true. And if we pretend for a moment that the number of distinct micro conditions in any given region of the phase space is proportional to the standard Lebesgue volume of that region, and this is just nonsense because there aren't numbers of such things, then it'll follow from the principle of indifference that I ought to proceed as if the statistical postulate is true. And the trouble with this, even if we agree to overlook the falsehood and the nonsense that I just mentioned, is that it isn't clear exactly what this admonition about how I ought to proceed is supposed to amount to. Here are two interpretations that come to mind. First interpretation: you ought to proceed as if the probability that the system is in any particular one of those states is 1 over n just means the probability that the system is in any particular one of those states is 1 over n. But this is preposterous for exactly the reasons that Valia said. This is to read the principle of indifference as asserting that there's some a priori connection between what I happen to know and the frequencies with which certain physical systems are in certain particular physical states out there in the world. And I don't think anybody believes anything like that. Second interpretation. You ought to, quote, you ought to proceed as if the probability that the system is in any particular one of those states is 1 over n means something like your credence that the system is in any particular one of those states ought to be 1 over n. But it seems to me that this gets us nowhere. The earlier thing would have gotten us what we wanted, but it's obviously false. This interpretation seems to me to get us nowhere. What we're looking for here, remember, is an explanation of the truth of the laws of thermodynamics, and nothing about what credences I happen to have or what credences I ought to have can play any role in explaining why certain things happen with certain probabilities out there in the world. This is maybe worth saying a little bit more carefully. The thought is that nothing about what credences I happen to have or what credences I ought to have can play any role in explaining why certain things happen with certain probabilities out there in the world, unless, of course, those credences or those obligations, together perhaps with certain other facts about the world, somehow entail those probabilities. But if that were the case, then the second interpretation would just reduce to the first interpretation, and we've already considered the first interpretation and dismissed it as preposterous. Yeah?
Can I just ask this question?
Sure.
When you say why certain things happen with certain probabilities out in the world,
Yeah.
which you just said a couple times,
Yeah.
does that mean with certain frequencies?
No. It means, I mean, it depends on your interpretation of probability. As I said a few minutes ago.
So it's not clear what it would mean to say something happens with a certain probability.
Well, for example, if you're a Humean, it is clear what it would mean. The world is such that, that is the way, the way events fall out in the world is such that
Then it's something about frequency.
it's something very, yeah, okay, good. It's something very indirectly about frequencies, but yes, that's right, that's right. Good. And that, insofar as I can tell, is that insofar as the principle of indifference is concerned. And nowadays, mind you, nobody would be caught dead defending the principle of indifference. But I guess I suspect, sorry. I didn't say caught alive. But I take it that many or many more, let's say, in the privacy of their philosophical consciences, believe something like that. The longing to reduce the statistical postulate to almost nothing. The longing, that is, to show that the work that the statistical postulate does in statistical mechanical explanations is something somehow akin to the work of logic or of reason or of some a priori and unassailable kind of common sense, is still very much alive and is, insofar as I can see, as confused as it was in the original case of the principle of indifference. Sometimes the conversation zeroes in on the nature of explanation. Someone insists that the fundamental hypothesis of statistical mechanics suffices in and of itself to explain why the laws of thermodynamics are probabilistically true. And if we object that the truth of the fundamental hypothesis of statistical mechanics does not in and of itself logically entail the truth, probabilistic or otherwise, of the laws of thermodynamics, we're told that explanation is not, or not always, or not necessarily, a matter of logical entailment. There's something of an art, we're told, to knowing when explanations are done. The thought, insofar as I can understand it, is that something has been satisfactorily explained once there are no longer reasonable grounds for being puzzled that the thing is true, and that where there are no reasonable grounds for puzzlement, no explanations are called for. And we're told that once the fundamental hypothesis of statistical mechanics is in place or has been made plausible, then no one in their right mind can any longer be puzzled that the laws of statistical mechanics are true. And I'm not sure what to say about this, other than it just seems radically wrong to me. It seems to me, to begin with, that there isn't any art in the context of fundamental and universal theories of nature to knowing when explanations are done, or to knowing what needs to be explained and what doesn't. Here, insofar as I understand it, is the deal. Every law-like empirical regularity of the world needs to be explained. And all such explanations end in exactly the same way and at exactly the same place. Every law-like empirical regularity of the world, in particular, must either be a fundamental empirical law of nature or must be logically entailed, perhaps in some appropriately conditional form, a form involving, for example, what Veronica Gomez refers to as crystallization phenomena, stuff like that, by the fundamental empirical laws of nature. That's what explanations look like, and that's what all explanations look like if the scientific project succeeds, insofar as I understand it, once all the fundamental laws are on the table. And the connection between the Lebesgue volume of phase space on the one hand and the actual tendencies of physical systems to evolve in this way or that on the other is not a matter of logic, and it's not a matter of pure reason, and it's not self-evident, and it's not a priori, and it's not susceptible of being further elucidated or explained by talk about how puzzled I am or how puzzled I ought to be. It is rather a connection that we learn, just as we learn the laws of dynamics from our empirical experience of the world. I've sometimes overheard people suggesting that the dynamics itself somehow logically entails that the right measure of what's probable or of what's typical is the Lebesgue volume. And by the way, it is true that I've overheard people suggesting this a lot. I don't know if this being defended in print, but it's worth putting on the table just to put out of the way before I get to something a little more subtle. If that were the case, that is, if it were the case that the dynamics by itself somehow logically entails that the right measure of what's probable or of what's typical is the Lebesgue volume, if that were the case, then it would be true that we learn the identity of this measure by empirical means. We learn it, that is, by the very same empirical means that we learn the laws of dynamics, and yet it would also be true that the only thing that we need to learn by empirical means in order to do statistical mechanics is those laws of dynamics themselves. I'm not sure, as I just said, that anybody has ever actually attempted to defend a claim like this in print, but it is, as I said, the sort of thing that one hears rumors about, and maybe it'll be worth taking a minute to put to rest. Here, insofar as I'm able to reconstruct it, is the idea. If the dynamical laws of the world are deterministic in both temporal directions, then it's a straightforward matter of logic that the probability that the actual microstate of the world at a certain time t1 belongs to a certain set of the world's possible microstates must be equal to the probability that the actual microstate of the world at any other time t2 belongs to the set of the world's possible microstates into which the original set evolves over the interval between t1 and t2 in accord with the dynamical laws. And it's a consequence of Liouville's theorem that the Lebesgue volume of the above-mentioned set of states at time t1 is equal to the Lebesgue volume of the set of states that those states evolve into at time t2. And the thought, if I can reconstruct it, is that if you put all that together, what you get is that Liouville's theorem logically entails that probability is proportional to Lebesgue volume. And the trouble is that although the first two of the previous three sentences are perfectly true, the third is just a non sequitur that doesn't follow from the first two at all. All that the first two sentences show is that for any region R1, there will be some region R2 whose volume is equal to R1 and whose probability at T2 is equal to the probability of R1 at T1. But it doesn't follow that, say, at T1, for any two regions R1 and R3, if their volumes are equal, then their probabilities are equal. And it doesn't even follow if it's stipulated that the probabilities of R1 and R3 at the earlier time are both non-zero. And indeed, it should have been clear from the word go that nothing of that kind could possibly have been true. No contradictions are going to arise, after all, from anybody starting with any probability distribution whatsoever and evolving that probability distribution into the future using any Hamiltonian dynamical laws they like. And so the dynamics cannot possibly have any implications as a strictly logical matter about the probability measure at some particular time. Good. Sometimes people will grant everything I've just said over the past 2 minutes, but we'll go on to say that the dynamical laws of classical mechanics nevertheless pick out the Lebesgue volume as the only reasonable measure of probability or of typicality, or as the preeminently natural measure of probability or of typicality, or something like that. And one hears all sorts of different things about what words like reasonable and natural are supposed to mean in this discussion. We heard, Valia referring to proposals that reasonable and natural in this context have something to do with time translation invariance, or something like that. But I just can't see why it should matter what words like reasonable and natural mean. I mean, so long as they mean anything other than empirically correct, they're just going to be of no use for our purposes here. And as we've seen, there's no way of inferring from the dynamical laws alone which particular probability or typicality measure turns out to be the empirically correct one. Good. Let me come back, and I'm going to get done quite early here. Let me come back now to the point that both Valia and I agreed to put to one side at the respective beginnings of our remarks, which is that the version of the statistical postulate that I've been focused on here, and the version of the statistical postulate that Valia was focused on in her talk, is, as a matter of fact, wildly empirically false. As I understand it, the most general and the most fundamental probability distribution that we have at our disposal in statistical mechanics, the one that we start with, the one that we go on to conditionalize on whatever we may happen to see or to be told or to remember of the world, is not the distribution that's uniform over the whole phase space, but the one that's uniform over only those regions of the phase space that are compatible with the past hypothesis. And for someone who thinks of these probability distributions as empirical laws, like I do, and apparently like Jean Brichemont does, none of this is going to amount to a particularly big deal. We start out with a simple guess about what the relevant law might be, and then we discover that that guess, as it stands, is in fact empirically false, and so we modify it. And that's just the sort of thing that happens, after all, in the normal course of scientific work. I'm not sure how all this is going to look, and maybe people can tell me, on the other hand, to someone who thinks that it's somehow self-evident or that it can somehow be deduced from the dynamics that the genuinely fundamental statistical mechanical probability distribution is the one that's uniform over the phase space as a whole. Are people like that going to be inclined to assert, for example, counterfactuals like, if not for the truth of the past hypothesis, the universe would have been very likely now to have been in equilibrium? It's hard for me to imagine what the empirical content of a claim like that, or what the empirical cash value of a claim like that could possibly be. Okay, I'm almost done. Let me just finish up by raising a puzzlement and by trying to provoke a conversation, I guess, about why it is that people find it so hard to stomach the idea that the statistical postulate is a bona fide freestanding empirical law of nature. Sometimes people say that the very idea of an objective physical probability that the universe had this or that particular initial condition makes no sense. The universe, they point out, happens only once and can have only one initial condition. And sometimes people say that the fundamental physical laws must necessarily have a dynamical character. Sometimes people say that something like the statistical postulate, which concerns questions of what conditions obtain at some particular time, rather than questions of how conditions at different times are related to one another, is simply not a candidate for a fundamental physical law. And I don't want to go into this in much detail, but in some way the whole workshop has been about such questions. I guess that I think that convictions like those have to do with an understanding that I disagree with about the sorts of things that laws of nature are. But like I said, an adequate defense of that claim would take me too far afield here and has been the subject of a lot of discussion here, and I'm happy for it to have more discussion now. But one can refer the interested reader to people like David Lewis and Barry and so on. Good. Sometimes, and a little more interestingly, I think, people say that the assignment of a precise and precisely Lebesgue uniform probability distribution over possible initial conditions of the universe gives us more information than the fundamental laws of physics ought rightly be expected to contain, and more information than maybe we need to do statistical mechanics. Once again, this is a point that Vallia was making. A distribution like that, when combined with the deterministic laws of motion, is after all going to assign a numerically precise probability to every single formulable proposition about the physical history of the universe. And many people have pointed out that this is probably a great deal more information than would actually be required in order to derive the laws of thermodynamics from the fundamental hypothesis of statistical mechanics. And many have said that it feels like more information than we could ever have any legitimate epistemic right to. And maybe that's right. I can think of ways to push back on that, but maybe that's right. Let's grant then, at least for the sake of argument, that we might indeed be able to do just as well, for all foreseeable scientific purposes, to start with a set of probability distributions over the possible initial microconditions of the universe, each of which is stipulated to be not too drastically different from the Lebesgue uniform one, and formulate our fundamental theory of the world as follows. The theory endorses all and only those propositions on which all of the distributions in the set happen to agree. A theory like that is not going to assign any perfectly determinate probability value to the proposition that this particular block of ice will be melted 10 minutes from now, or that we're sitting here in this room, or anything like that. But it will nevertheless assert that it's very likely or very typical that the ice will be melted 10 minutes from now, and that it's typical for blocks of ice in these sorts of macroscopic situations, I'm sorry, I'm repeating myself, to be melted 10 minutes from now, and that there will be no reason to be surprised if we come back 10 minutes from now and find that the ice has melted, and so on. And it might be considered an advantage of a theory like that it speaks of nature not in the language of probability, but only in the less precise and less informative, but perhaps more scientifically appropriate language of typicality, or of usualness, or of unsurprisingness, or something like that. But it should be clear that none of this is going to make the slightest bit of difference to the question of whether the statistical postulate, whether it's formulated in terms of probability or typicality or usualness or what have you, can be anything other than a fundamental empirical law. After all, the range of different probability distributions that should be included in our set, and the fact that those distributions all need to be not too far from the Lebesgue uniform distribution, are once again going to be things that we learn empirically and not a priori and not from the microscopic laws of motion by themselves. Thanks.